Hello and welcome to Techmar's product training for advanced heat pump control for radiant heating and cooling applications. My name is Elizabeth Brown. I am a technical support specialist here at Techmar Controls, and I will be your instructor for this course. I'm sure most of you are familiar with Techmar Controls. We are located in Vernon, British Columbia, Canada, and we are part of the Watts Water Technologies family. Now, Techmar designs and manufactures controls mostly for hydronic applications, so certainly my expertise is on the control side. However, if you have looked at the overviews for each of the 6 modules in this course, you will have noticed that we developed this course to include an overview of each of the components in a geothermal system design. And the reason we structured the course that way is because the control solution depends on the proper geothermal system design, and that includes a properly designed ground heat exchanger, properly designed and selected equipment in the mechanical room, and a properly designed distribution system. So the control system has to work together with each of those components to provide you the type of geothermal system that you're expecting. So it's for that reason that we do have an overview of essential design elements for each of those 3 components. It's been great to see the type of students that have signed up for this course. I've been very impressed with your backgrounds, with your experience level and your interests. So I just want to say up front that if there's anything that you are looking at learning that I might not have addressed in the course or I haven't addressed in the detail you're looking for, please feel free to send me a message and I can answer your questions individually offline. And certainly as the course goes along, if you bring up something that I think may be of interest to other students, I can try to incorporate it as we go along as well. So this first module is going to be an overview of radiant heating and cooling. Now I know all of you are familiar with radiant heating and cooling to some extent as well, although radiant cooling has gained popularity in recent years, especially in North America. And we're going to look at that in particular in this course. And look at how it works, what are the benefits of a year-round radiant system, and we'll look at what are some challenges that we need to address in this training and myths of radiant cooling that we need to overcome. So here's the outline of the course. You can see we're going to start by how does a radiant heating and cooling system work? What are the principles in a radiant system? We'll look at the benefits that a heating and cooling system can provide and what are challenges that we need to address in this course. Some of you have even brought challenges to my attention through the message wall already, which has been great. We'll look at the myths of radiant cooling. So there are certainly a lot of myths that we have to overcome, and those myths are out there because of poorly designed systems. So certainly when we have a properly designed system, we don't encounter any of those obstacles that people bring to your attention immediately when you even discuss the subject of radiant cooling. We'll look at what are some keys to the proper operation of a radiant heating and cooling system, and we'll briefly touch on some of the control strategies. Now, one of the greatest things about using a radiant system for heating and cooling is that it's a system that you use year-round. So why design a system that you can only use for half of the year when you can use that infrastructure year-round? I often get asked if radiant heating and cooling work in the same way. And the key to understanding that is understanding how radiant heat moves. So it always moves in one direction and one direction only, from warmer surfaces to colder surfaces. So when we talk about radiant heating, we have hot water circulating in our tubing, which warms the floor. And the floor will radiate heat to any objects in the room that are at a lower temperature, including the person we see standing in the middle of the room there. Radiant cooling works in the opposite fashion. Now we have chilled water circulating through the tubing, and the occupant that's in the room is at a higher temperature than the floor. So he or she will have heat radiating from their bodies to the floor itself. So the direction of heat is always from warmest to coldest. But in radiant heating, we have the heat radiating to the occupant and the objects in the room. And in radiant cooling, the occupants and objects in the room have heat radiating from them into the floor. We're going to go over the benefits of a radiant heating and cooling system. Now, usually these systems are designed for three different reasons: for efficiency, for comfort, and because customers are asking for them. And when I say customers are asking for them, the reasons that we'll go into are those reasons that are in addition to the efficiency and the comfort. So radiant systems, as we know, are more expensive to install than strictly a forced air system. And so the benefits have to be compelling for homeowners or designers to choose to install them over a strictly forced air system. And we're going to look at what those benefits could be. When we talk about efficiency, there are three major points that we're going to cover. The first is year-round operation. So if we are going to install a radiant system, why have it just be for heating when we could have it for heating and cooling? And what are the benefits of having one installation used throughout the entire year? Next, we'll look at energy consumption. So how are water and air different as energy transport mediums? How is the power consumption for pumps and fans different? And how does a radiant system allow us to adjust the room set points and maintain the same level of comfort? We'll look at all of those points. The last point we're going to cover under efficiency is the forced air system. So radiant systems are typically installed with a forced air system. And the reason for that is that in heating mode, radiant heating typically cannot provide all of the heating needs of the space. And in cooling, we can only address the sensible cooling load. We can't address the latent cooling load. So for those reasons, a radiant heating and cooling system will be paired with a forced air system. Now the forced air system, because we have that radiant base load taken care of, can be designed much smaller, and we'll look at how that contributes to a more efficient heating and cooling operation in the coming slides. One of the reasons a radiant heating and cooling system is so efficient is that we can use it year-round. So it's certainly leading customers to ask more about radiant cooling if they're already interested in installing a radiant heating system. The obvious question is, why not design a system that I can use year-round rather than just for the heating season alone? There are all sorts of advantages to that. It would allow us to be less reliant on our forced air system. So we were operating our furnace less, we're an air conditioner less. The year-round usage capability of a radiant heating and cooling system certainly speaks to the efficiency of this system. Now, as far as energy consumption is concerned, the first piece of the puzzle is the differences between water and air and how they can transport heat in different amounts. So we need to look at the heat capacity of each of these mediums. Now for water, the heat capacity is 62.4 BTU per cubic foot degree Fahrenheit. For air, our heat capacity is 0.018. Now that is a difference of almost 3,500. What that means is that water can absorb almost 3,500 times as much heat as the exact same volume of air. And to look at an image that really depicts this well, down here we have the amount of water that it would take to transport a certain amount of heat versus the amount of air. So we're looking at a 3/4 inch tube versus an 18-inch duct. It's quite a big difference. Here we have the 3/4 inch tube with a rectangular duct that is 20 by 12. So we can see the difference in the capabilities of these two mediums at transporting heat. So if we are looking at space concerns, it's much more efficient to design a system with tubing than it is to install large ductwork throughout the building. So certainly the ability of water to transport heat versus air is one of the reasons that people are considering radiant heating and cooling in greater numbers. The next piece of this puzzle is the energy consumption between pumps and fans. So if we look at this pie chart here, we can see in red the amount of fan energy versus pump energy in blue. So heat can be transported hydronically to or from a space with circulators using significantly less energy than transporting that same amount of energy in an air system with fans. Now that is because the heat transfer capacity of water is much higher than air. As we saw in the previous slide, the heat capacity of water is almost 3,500 times the heat capacity of air. So what that means is to transport a certain amount of energy, we need to move a much smaller volume of water than we do air. So because we're moving much smaller volume of water, the pump energy that it takes to move that amount of water is much lower than the fan energy it takes to transport the larger volume of air. It's also because fans are operating at significantly higher wattages than hydronic distribution systems. So pumps are typically operating at less than 10% of the wattage than fans. So those two factors together really speak to how efficient it is to transport heat hydronically versus through a forced air system. Particularly when we talk about cooling, because peak cooling has become a bit of an issue in North America. We've had problems meeting the demand with the appropriate supply when we're talking about peak cooling times in North America. So to be able to reduce that peak cooling demand by satisfying a baseload portion of it with radiant cooling would make the system much more efficient and alleviate some of the demand from our grids. I did mention earlier that radiant systems allow us to have more conservative air set points. So if we're talking about radiant heating, because we have a warm floor, we can have a lower air set point while maintaining the exact same level of occupant comfort as if we'd had no heated slab with a higher air set point. So because of the offset from that heated slab, we can reduce our air set point and have the same level of comfort. In cooling, because if we have a chilled slab, we can have a higher air set point and that same level of occupant comfort because of the offset of the cooled slab this time. So having more conservative air temperatures certainly will reduce our ductwork distribution losses from the air side, and speaks again to the increased efficiency of having a combined radiant and air system. The final point that speaks to the efficiency of a radiant heating and cooling system is that we can downsize the forced air system. So as we mentioned earlier, a forced air system is still needed to complement a radiant system, and that is because in heating mode, we typically can't satisfy the needs of a building space with radiant heating alone. And in radiant cooling, we can only address the sensible cooling. We cannot remove humidity with radiant cooling. So for those reasons, we do need to add a forced air system. But because we have that radiant system taking care of the base load of our heating and cooling needs, the air system can be downsized significantly. So we need smaller ductwork, the blower can be sized much smaller, and so can the equipment, the furnace and the air conditioner. Another reason that customers are asking more about radiant heating and cooling systems is because of the increased thermal comfort that they offer. So we all know that warm feet is the typical slogan for radiant heating systems, and that certainly speaks to occupant comfort. But going beyond that, the ASHRAE Standard 55-2010 lists 4 items as being key to thermal comfort. Now these are the environmental items only. So those 4 points are the radiant temperature, the air temperature, the humidity, and the air velocity. Now if we're looking at a forced air system alone, well, we can address air temperature, humidity, and velocity, but we do nothing for radiant temperature. Likewise, if we're talking about a radiant system, we can have an impact on radiant temperature, and air velocity, but we can't do anything about humidity. So it's only through combining a radiant and forced air system that we can address all 4 of those items in the ASHRAE standard. Next, we're going to talk about operative temperature and how that affects the thermal comfort. So to do this, we're looking at a graph, and it's based on the ASHRAE Standard 55 that we mentioned on the previous slide. On the left-hand side, we have the humidity ratio, and it's actually also represented by a relative humidity percentage as well. We have the operative temperature on the bottom of the graph, and on the right-hand side, we have the dew point temperature. Now, you may not be familiar with the term operative temperature, but the 2 main parameters for thermal comfort in a radiant application are the air temperature and something we call the mean radiant temperature. And the combined effect of these 2 parameters is expressed as the operative temperature. And the operative temperature is a good indication of whether or not an occupant will feel comfortable. So for optimal comfort, we want our operative temperature to be somewhere within the blue in the winter and within the red in the summer. And the reason we have separated the temperatures between winter and summer is because of the difference in the type of clothing people wear in the winter and summer months. So in the winter, we are looking at operative temperatures that correspond with this blue section. Now, if we isolate that to include the optimal comfort based on relative humidity, we can say relative humidity is best when it's between 20 and 60%. So here's my yellow line for 20% and my yellow line for 60%. So to keep within these 2 parameters, we are looking for operative temperatures in this space. So as long as the operative temperature in the winter is between, let's say, 68 all the way to 77, 78, then the occupant will be comfortable. If I look at the summer and I stay between my 20 and 60%, then my operative temperature can range from, let's say, 76 all the way up to 82. We're going to look more at operative temperature on the next slide, but keep in mind for the winter months, the operative temperature that will provide the greatest comfort can range between 68 and, let's say, 78. So as I said, operative temperature is the average of the room temperature and the mean radiant temperature. Now, mean radiant temperature is the combined effect of all the surfaces that would radiate heat to the occupant. So it would be the walls, it would be doors, windows, all these have an effect on the mean radiant temperature. For the sake of this example, we're just going to be looking at the floor. So our floor in this case has been heated to 80 degrees Fahrenheit, and my room air temperature is 68 degrees Fahrenheit. So to summarize operative temperature, what that means is when we have a combined radiant and forced air system, we can have heated floors In this case, we're in the winter season, so we have heated floors and reduced room air set points. And the combined effect is a temperature that is directly related to thermal comfort, that operative temperature. And as long as that operative temperature is within the suitable range, then we know we are maintaining occupant comfort. To calculate operative temperature, we add the air temperature to the mean radiant temperature and divide by 2. Now, as stated previously, for this example, we're only going to consider the floor temperature. We're not going to consider the radiant temperature of the other surfaces in the room, like walls, windows, doors, etc. So for the sake of this example, the operative temperature will be 68 degrees Fahrenheit, which is our current room temperature, plus 80 degrees Fahrenheit, which is our current floor temperature, divided by 2. Giving us an operative temperature of 74 degrees Fahrenheit. And of course, that is well within our comfortable range as shown on the chart on the previous slide. The other benefit of a radiant system in terms of thermal comfort is that the temperature profile is constant, compared to a forced air system where the temperature profile is very variable throughout the space. So if I'm looking at the left-hand side, I can see I have a baseboard convector here. The circulating water to that baseboard convector would be about 140 degrees Fahrenheit. And through convection, I'm going to induce air currents, and the temperature is going to change along that current. So you can see as it moves up, at this point in the room, the air temperature would be about 70 degrees. The hottest point is going to be at the ceiling at 84, and the air will get cooler as we move down. So the air close to the floor would be about 64 degrees in this example. So you can see we have a stratified air system where the hottest air is going to be close to the ceiling, and as we move down, the air temperature will get colder. It also means we're going to have the greatest heat loss at the ceiling, which we of course want to avoid. If I compare that with a radiant system, I have a very stable temperature profile. So close to the flooring, you can see the air temperature would be 77. As I get higher, it's changed to 70, and the ceiling is 68. So I don't have that heat loss at the ceiling. The heat is actually concentrated at the level where the occupants are located, which makes sense, doesn't it? Why not have the greatest temperature of air where the people in the space are going to be located? Because they're not at the ceiling. So that's why we say that radiant heating and cooling will offer more effective space conditioning, because we're actually putting heat where it's needed, and we're not putting it where it's not needed. Another point that speaks to the enhanced thermal comfort that a radiant system provides is that there is less forced air. And what I mean by that is the forced air system is used less often because that base load of heating or cooling is being addressed by the radiant system. And one of the most common complaints that we hear from owners of forced air heating or cooling systems is the amount of dust and airborne pollutants that are distributed through the building, through the ventilation system. So we can reduce that by becoming less reliant on a forced air system with the installation of a radiant system instead. The other benefits that we'll encounter with reduced reliance on a forced air system is that there's less noise. There's going to be less draft as well. So these are all points that speak to the enhanced thermal comfort that a radiant system can provide by becoming less reliant on the forced air system side. Now I mentioned demand earlier. So one of the reasons that more radiant systems are being installed is because people are asking about them. And of course they're asking for them in terms of efficiency and comfort, but there are other reasons as well. People are interested in reducing their energy costs. The reduction in energy costs is tied to the increased efficiency of a radiant system over a forced air system. And we saw earlier in the presentation that the heat capacity of water is nearly 3,500 times the heat capacity of air. So we are able to provide the thermal conditioning to a space using water at a fraction of the energy that it takes to provide that same conditioning using forced air alone. There's also interest from designers because of the architectural appeal of downsizing the forced air system. So you can see in the image here, this ductwork is quite pronounced in this space. So the architectural appeal of not having this big ductwork in a space speaks to designers. The other demand factor is zoning. So now that people are becoming more concerned about energy efficiency and placing greater emphasis on comfort, the topic of zoning comes up a lot. So why not concentrate heat where we need it, when we need it, instead of recklessly, needlessly heating an entire space to the same temperature when it doesn't have the same occupancy. So these are all the reasons why there is a demand for radiant heating and cooling systems that extends beyond just efficiency and comfort. Of course, there are challenges with radiant heating and cooling systems. And these are challenges that students have brought to my attention already in this course. We are going to address all of these challenges throughout the course because these are the first roadblocks that a lot of people have. So passive solar gain is a big topic when we're talking about radiant systems. How do I control a radiant which has a large thermal mass when I have potentially a lot of glazing in that space? So how do I control the radiant when I have such potentially high solar gains as well? And we will discuss that in this course. And that has to do with the high thermal mass of radiant heating. So because that slab is going to be radiating heat long after we stop delivering heat to the slab, how can we control that to make sure we're not overheating or underheating a space? What we don't want are uncomfortable temperature swings, and a high thermal mass can be a challenge when it comes to avoiding temperature swings. So again, that comes down to design and control, and we will get to that point as well in this course. The other challenge is people are asking, well, what is the capacity of the ground heat exchanger? So when we're talking radiant cooling and heating systems, we are talking geothermal. And there is a lot of confusion out there about how we can size our geothermal so it does provide the heating and cooling that's needed. And if it doesn't, how do we design to take that into account? We've all heard about bad geothermal designs where we are depleting the ground source energy. So we are taking more energy than we're putting back into the system. And that's a design issue that even the best controls can't overcome. So the solution to that would be to design appropriately from the start. And we'll talk about that more in this course as well. Another challenge is the heating and cooling interlock. So you want to make sure, of course, that when thermostats are calling for heating, we're not sending chilled water to the system and vice versa. And this is something, again, that will come down to control. In the past, when people have had bad results with the heating and cooling interlock, it's been because they didn't have the suitable control. They were instead trying to use relays and electrical interventions to try to turn circulators or valves on and off and prevent certain zones from heating when they were calling for cooling and vice versa. So the control is the answer in addressing the heating and cooling interlock. And of course, we'll talk about that in greater detail in this presentation. And lastly, the challenge that we hear a lot of the time is, well, what about humidity? And that's a very valid concern because radiant systems cannot address humidity. So we need to design the heating and cooling system with humidity control in mind. And we have to be very mindful of that humidity when we're talking about radiant cooling, because we always make sure that there is no chance of condensation. And so that comes down to the sophisticated control algorithms that are in place to take into account what the relative humidity measurement is and then adjust the water temperatures accordingly. Now, when we talk about radiant cooling, a lot of people immediately counter. Well, that's not a good idea because of condensation. Or I've heard that radiant cooling may be uncomfortable because the floors are too cold, or it's only suitable in dry climates. So we're going to look at each of the myths of radiant cooling and learn why those myths may have started in the first place and how we can dismantle the myth when we talk about appropriate control and design. So let's start with the myth of radiant cooling capacity. As radiant heating and cooling has grown in popularity and we see more and more applications, we're starting to get more reliable data. But there is a lot of bad data out there that has led to some misunderstandings of what kind of capacity radiant cooling can offer. Typically, we're looking at 7 to 14 BTU per square foot. Now, where we see the greatest impact are in areas that have a lot of glazing. So if I look at this image on this slide, I can see this is a space with a lot of window area. And it's going to experience a lot of solar gain. And that's where radiant cooling offers the greatest capacity. Up to 32 BTU per square foot can be observed in areas of high solar gain. Now, it is important to understand the capacity when we are designing the entire system. So you have to have realistic numbers to work with so that you know what kind of forced air system you need to address the entire cooling load. Condensation has to be one of the greatest obstacles when we start talking about radiant cooling. And it's important to remember that a well-controlled radiant system will never experience condensation. The way we do that is by constantly measuring the relative humidity in the space. And once we have that relative humidity measurement, a control is able to use that measurement to calculate the dew point temperature in the room. If our target water temperature was ever to be below that dew point, it would automatically be adjusted. And that's something we call dew point reset that we'll talk about more throughout this course. So we always make sure that our supply temperature is above the dew point temperature of the room by at least 2 degrees. Certainly the myth of condensation is something that we need to address right away whenever we start talking about radiant cooling. And the key to tell people is that if you have the proper design, the proper installation, and the proper control, you will not experience condensation. But it does rely on having the proper system design, the proper installations, and of course the proper control to make sure that we are monitoring that relative humidity, calculating the dew point, and making sure we are always above that dew point temperature. Now, a lot of people say, well, you can only use radiant cooling in a dry climate. This doesn't work for humid climates. Well, that's just not true. The picture I have shown here is the Bangkok airport in Thailand. This is obviously a very hot and humid location, and they were able to implement radiant cooling in the design of this airport. You can see there is a lot of window area in this airport. And so when they were designing this, they knew that there would be a very high level of solar gains. And a forced air system would just not be efficient when we talk about how large this space is. So you can see we have very high ceilings, very open space, and it wouldn't be suitable for a forced air system alone. So they designed this system to have radiant cooling, and the radiant cooling whisks away those solar gains before they have a chance to heat the space. So this was a very well designed, implemented radiant cooling system where it was done in a location that is very hot and humid, but done in such a way that it was only trying to remove the solar gains and not provide any latent cooling. So a forced air system is of course still needed to remove that humidity in the space, but we can reduce the overall cooling load by whisking away those solar gains with the radiant cooling. Now, I did mention throughout this module so far that a radiant heating and cooling system can only overcome those challenges and those myths if it's operated properly. So what do we need to make a radiant heating and cooling system operate as intended and meet those customer expectations? Well, the first thing you've heard me say over and over again at this point is that it's essential to have a combined air and hydronic system. So the radiant heating typically can provide all the heating needs, and the radiant cooling can only address typically part of the sensible cooling load. We have to think of the overall cooling load, and in particular that latent cooling load, that humidity. So a forced air system is always strongly recommended. The next is that humidity control. We talked about the myth of condensation, and the only way that we can properly control that and make sure that condensation doesn't happen is when we are monitoring the relative humidity in the space so that we can make sure the water temperatures are sufficiently high that condensation never occurs. So a control solution must include relative humidity measurement. If we don't measure it, we can't control it, and you will have dissatisfied customers, and certainly without relative humidity control, condensation will be an issue. Now, one of the reasons that we do want to monitor relative humidity is for the dew point reset. So addressing concerns about condensation, we will measure the relative humidity, calculate the dew point in that space, and make sure we are always above the dew point temperature. So you can see here the pairing between relative humidity and dew point reset. That's got to be in your radiant heat cool control strategy. To summarize our first module, we looked at radiant heating and cooling, how it works, what the benefits of a radiant system are, and what the challenges are. And the challenges are very important to address. These are the first obstacles you're going to encounter when you start talking to people about it, when you start designing systems, when you're trying to make sure that you're going to meet customer expectations. Next, we talked about the myths of radiant cooling, and those myths are there for a reason. They are around because of badly designed systems. And so, now we have to make sure we address those thoughts of radiant cooling that are out there and reassure people that a properly designed system with the proper controls means you won't experience those negative associations that some people have with radiant cooling. We talked a little bit about the proper operation, and the big takeaway there is that a radiant system must be combined with a forced air system. So don't install a radiant heating or cooling system on its own. We need it typically for the heating side to satisfy the heating load. And we definitely need it when we talk about radiant cooling to address the latent cooling load, and potentially to provide part of the sensible cooling load as well. And we'll talk about these more later in the presentation when we dive into the control points of the Tecmar controls 406 and 557. And lastly, in this module, we looked at some control strategies. Really the big ones here are the humidity control and the dew point reset. So the control strategy has got to have those points, or the radiant cooling system will disappoint the homeowner. We're coming to the end of this first module in the Advanced Heat Pump Control Training for Radiant Heating and Cooling course. If there is any one of those points that you would like me to elaborate on, or you have a question that might have been partly answered but you would like more information on, please feel free to send me a message and I'll get back to you right away on that. And I look forward to talking to you again and when we start the second module of this course, where we're going to look at the geothermal side and the advantages of having a water-to-water heat pump for our radiant heat cool application. So thank you very much. Again, feel free to send me any questions that you may have or ask for any additional guidance. I'm happy to provide it.